Today let us discuss about Kepler's laws of planetary orbit. Kepler gave these laws mainly for all the planets surrounding Sun. From Newtonian mechanics we have the law of planetary motion like this, popularly known as inverse square law, as the acceleration is inversely proportional to the square of the radius. Here this m is the mass of the Sun, small m is the mass of the planet, and r denotes the length of the radius vector from Sun to the respective planet. Okay, Kepler stated three laws relating to the motion of all the planets around the Sun. Actually, Kepler's first law states that all the planets revolve around the Sun in an elliptic orbit with Sun at any one of its foci, either this focus or this focus. We all know that in elliptic path we have this as the center, this as the major axis, and this as the minor axis, and these are the two focus. So Kepler's first law states that each planet rotates in an elliptic path with Sun at any one of its focus. And the second law of Kepler states that this radius vector from Sun to the planet sweeps out equal area in equal time. Okay. What does it mean? Let us explain. We may assume that this planet moves from this position P to this position P prime, say in time t. So the radius vector from the Sun to the planet sweeps out this area, isn't it so? The radius vector sweeps out this area, P is P prime. Now we assume that it moves from P double prime to P triple prime in the same time window t. Then this area, these two area rather, P double prime S P triple prime, will be equal to this area. So the rate of sweeping out the stressed out part of the radius vector will be constant, isn't it so? Second law states that this radius vector sweeps out area in constant rate. Okay, and what about the third law? Third law is very simple. The square of the time period varies as cube of the semi-major axis. Semi-major, this is the major axis and this is semi-major axis. The square of the time period varies as cube of the semi-major axis. So these are the three laws of Kepler, and we will discuss them in the light of what we have learned in radial and cross-radial acceleration for a particle moving under central force. we all know that the motion of the planets around the sun is according to central force, central orbit rather, because the force on the planet, force exerted by the sun to the planet, is always directed towards sun. And let us take that as origin, and since the force acts always towards O, so this is the radius vector OP is the radius vector, and cross radial acceleration 1 by r ddt of r square theta dot is actually obviously becomes 0. Force acts along the radius, there is no part perpendicular to it or no part along the cross radial direction, and we have the cross radial acceleration as 0. Since cross radial acceleration is 0, we have r square theta dot to be a constant of time. It doesn't change with respect to time. Since ddt of r square theta dot is 0, r square theta dot must be constant of time. And now let us take a look at this picture. So this is O, this is P having coordinate r and theta. So this measures r and POX measures theta. Okay, and this is a shifted position. The position P shifts to P prime in a infinitesimal small time delta t. That means P and P prime are infinitesimally close along the path. So P prime has coordinate r plus delta and theta plus delta theta. This is the coordinate. Okay. So obviously OP prime is r plus delta. This measures r plus delta, and this angle is delta theta. So this is a very simple geometry. If we drop a perpendicular Pn from P upon OP prime, we can easily see that, and join this PP prime, which is the chord PP prime. Actually, as P prime and P gets closer, this PP prime chord merges with the tangent at P. Now the area of the triangle POP prime, or we may write it as OPP prime, it becomes half base. Base is nothing but OP prime, which is r plus delta r, and perpendicular is Pn. And since this is delta theta and this is r, OP is r, everything, OP is r. So this is delta theta and this is 90 degree. So obviously perpendicular by hypotenuse is sine delta theta, and the measurement of Pn becomes r sine delta theta. So what is the area per unit time? For that we divide this area delta OPP prime area by delta t, and it becomes half r plus delta r sine delta theta by delta t. Okay, very simple application of limit. So the rate of change of area, sectorial area, rate of change of sectorial area traced out by the radius vector r OP. We may say rate of change of sectorial area traced out by this radius vector OP turns out to be this. We take the limit as delta t tends to 0, delta theta also tends to 0, and we adjust it by delta theta. We divide with delta theta and multiply with it, so that sine delta theta by delta theta becomes 1 as delta theta tends to 0, and we ignore this delta r into delta theta term in comparison with r into delta theta, so that this becomes, let us take a clearer look at this expression. This is nothing but let us take this limit as delta t tends to 0, we have delta theta also tending to 0, and this is nothing but r plus delta r. Sin delta theta by delta theta is actually 1 as delta theta tends to 0, so we replace this with delta theta by delta t, and then we see that r into delta theta is much larger than delta r into delta theta, because they both are infinitesimally small, so their product will be much more small than r into delta theta, and we ignore it. So it becomes, after taking the limit, it becomes half r plus delta r into theta dot. So this becomes, I missed this r here. So this should be written here. So this becomes half r squared theta dot, the very term which is r squared theta dot, or constant of time. So we have proved the second law, which states that the radius vector sweeps out equal area in equal time. The area turns out to be half r squared theta dot, which is actually a constant of time. The first law is actually a direct consequence of the fact that we have the pedal equation h square by p cube dp dr is equal to f, and as we know that this force is inverse square law, we may write it like this: mu by r square, and from here we can easily find that h square by mu dp by p cube is nothing but dr by r square, and if we integrate them, then it becomes h square by mu, and this becomes p to the power minus 3 plus 1 by minus 3 plus 1, and this becomes minus 1 upon r plus constant of integration c. Okay, and this becomes, we adjust this minus sign here, a 2 comes, and we keep it as h square by mu p square. This is actually 1 by p square, and this becomes 2 mu by r minus c. Okay, and from this equation, comparing with b square by p square equal to 2a by r plus minus 1 as the equation of ellipse or hyperbola in case of pedal equation, this p is the actually perpendicular upon the tangent, we all know from origin. This is the tangent pt, and this length is p, which is actually r sine phi, where phi is the angle between this radius vector and the tangent. So employing this, we can easily establish that Kepler's first law, which states that depending on the initial condition, whenever the orbit is a closed orbit or elliptic orbit, we have the sun at one of its focus. Now let us come to the third law. In case of Kepler's third law, we have t varies as a to the power 3 by 2, or we may say that t square varies as a cube. This can easily be proved with the consideration that area of ellipse, if this is the semi-major axis and this is the semi-minor axis, the area will be pi ab, and since the time period is pi ab by h by 2, where h is actually r square theta dot, the constant of time we all know, or the angular momentum, moment of linear momentum. R square theta dot may be shown to be the, just consider this picture. This is O, this is P, this is PT, and this is R, and we know that the radial velocities are dot and cross radial velocities are theta dot. Since r theta dot is perpendicular to r, so obviously the moment of momentum is r into r theta dot, which is r square theta dot, or the conserved quantity h. And the time period is obviously calculated with this formula, since pi ab is the total area of the ellipse and the rate of sweeping out this radius vector sp is h by 2, half r square theta dot. You remember we have shown that the rate of tracing out area by this radius vector is nothing but half r square theta dot, or 2h, h by 2. So this is time period, the total area divided by the rate, and it turns out to be 2 pi by root mu into b square by a into ab. Why? Because of this h square by p cube dptr equal to mu by r square. This is the equation, and from which we get that h square by mu is actually semi-lattice rectum. Whenever we have integrated, there is a 2 mu here, isn't it so? H square by p square equal to 2 by r plus constant, 2 mu by r rather. So obviously whenever we are comparing this with b square by p square equal to 2a by r plus minus 1, we can easily see that this h square is nothing but mu b square by a. So h is mu root over mu b square by a. So from this relation we can easily infer that h is nothing but root mu b square by a, semi-lattice rectum. L is the semi-lattice rectum, b square by a, and h is actually root mu L. These are relations we get from the central orbit equations only. So this becomes 2 pi over root mu, and this b and b cancels out, and it becomes a to the power 3n. So straight away we find this. Okay. So these are the 3 laws of Kepler and their deduction with the help of central orbit formula. Thank you.